Let's look at a couple examples of integration by substitution. This technique is a very important one among our integration techniques, some of which come in this course, some of which you would see in a future course if you continue with calculus. But integration by substitution is a really important one to know and a somewhat difficult one um, to become confident with. It takes practice. So my number one suggestion with integration by substitution is you really need to look at a lot of examples, practice with a lot of examples. The reason for that, or a reason for that, is that there's a wide variety of examples that lend themselves to this technique, and they can look very different from each other. The process is the same, but the type of integral that you begin with has a lot of variation. They don't have to resemble each other at all. And the two examples I picked out here, I think demonstrate that a little bit, where, they really don't look very similar, but they both involve this technique. Now, I'm not going to use this video to describe the technique itself, other than in the context of these examples. But let me point out what we're doing here, and I think as we go through this, you'll see, what the similarities are. We are substituting for something that we're calling u, and what you'll always see in a substitution example is that the derivative of u should also be represented in that expression, or perhaps a constant multiple of it. Let's see how that comes up here and why that's so vital to this process. So if we call u x squared minus 1, we know the derivative of x squared minus 1 is 2x. So under here, I'm using those differentials that we saw in chapter 4 to say du is 2x dx. Okay, u is this function, du is that derivative of that function times dx. And what that's going to allow us to do is to replace the original integral with a new one that only involves our new variable u. So this x squared minus 1 to the 99th becomes u to the 99th. But we also have to be mindful of everything else that we started with, the 2x dx. And it just happens to work out here that du is 2x dx. So the 2x dx becomes our du. Okay, so this happened to work out pretty nicely. Some of them work out a little less nicely because of a constant multiple that we have to account for. But here our new integral is u to the 99th du. And the goal is always to end up with a new integral that's easier to work with. Okay? Otherwise, why are we doing this technique if it's not helping us, right? So we want to start with something that's challenging to work with and end up with something that's less challenging. This one, we only need the power rule for antiderivatives. Just remember, at the end of this process here, we want to end up with our family of antiderivatives in terms of the original variable x. So we don't want to leave our answer in terms of u. And that's why we do that last substitution in order to get back in terms of x. The check with this, just like anytime we're doing finding antiderivatives, the check would be to take the derivative of this answer, and it should give us back the integrand that we started with. Let's move on to this one, which is a definite integral. And as I said, it looks quite different than the original, than this first example. But if we look closely at the expression we have here, we notice under the square root down here, we have tangent x plus 3. The derivative of that is secant squared x. And remember I said what we call u, we should see a constant multiple of its derivative in the expression as well, to have the possibility of this substitution technique of working. So u is tangent x plus 3, du secant squared x dx, and when we do those substitutions, we get a comparatively nicer integral to work with. It's just a power of u. It's a fractional power and it's a negative power, but it's a power of u. So it's a nicer, less challenging expression to work with than we started with. Now, I want to point out something here that you may have noticed and may be wondering about. Notice our limits of integration. We started with 0 and pi over 4, and now we have 3 and 4. Well, how did that happen? Well, let me explain. The original limits of integration are limits for x. This means x equals 0, and this means x equals pi over 4. But our new integral is in terms of u, not x. So our new limit should be in terms of u. So what we have to ask ourselves is, well, when x is equal to 0, what is u equal to? And so if I substitute in 0 for x, I get out 3 for u. And if I substitute in pi over 4 for x, I get out 4 for u. So that's why those limits are different. That is something to keep in mind when you have a definite integral. Okay, so we continue through this process. I just rewrote the u to the negative 1/2 in place of what we had up here. Then I found the antiderivative so that I can use the fundamental theorem of calculus. And then we go through and finish that process. Notice I never went back to x. And that's a difference between working with an indefinite integral and working with a definite integral when you're doing substitution. We can keep in terms of u till the end of the process until we apply the fundamental theorem of calculus, as long as we change those limits. So that was what allowed us to never go back to x. If you prefer, I don't necessarily recommend this, but it would technically be okay. In fact, I remember doing it this way when I was first learning this process. You can go through to this point, go back to x and use the original limits of integration. That'll give you the same answer. I don't think it's worth it to do that. I mean, unless for some reason you are struggling with this part of changing the limits. I think changing the limits to the new variable and then remaining with that variable is gonna, once you get used to it, that's gonna make things easier, save you a couple steps. But again, if you went back to x, you could use the original limits. I just don't recommend that. So those are two examples of integration by substitution. Again, you're going to want to look at plenty of examples and practice, and I think you'll find with some practice, this process will become more and more comfortable to you. I hope you found this helpful, and I'll see you in the next video.